Hello everyone, good evening. Welcome to our final presentation made for Geospatial Lab Advanced GIS course Fall 2022. This presentation is hosted by myself, Mousume Azad, and my other team members Marina, Riddle, and Doan. We all are graduate students of Environmental Management program at the University of San Francisco. Our study area located in San Diego County, as it is the second most populous county in the US, it requires a huge amount of drinking water. To solve this problem, the county officials built desalination plant to convert seawater into drinking water. In this map, the apple green highlighted area is the area where the Carlsbad desalination plant is located. Our project is a continuation from our intermediate GIS, which analyzed how many solar projects would be required in order to power the Carlsbad desalination plant. From our previous calculation, we found that in order for daily operation, the plant requires 750,000 kilowatt of energy. The suitable solar project only accounted for approximately 161,000 kilowatt of energy, which leaves 589,000 kilowatt of energy required in order to power the plant. A geospatial analysis of wind energy was performed in order to make up for this deficit.
For the method, we use Model Builder in ArcGIS to do weighted sum analysis. There was 5 criteria considered to analyze the most optimal location to place wind turbine: distance to row, population density, protected area, wind speed, and distance to transmission line. For all of our reclassify, we set the scale from 1 to 5, 5 being the best and 1 being the worst. It is optimal for wind turbine to be close to the road for regular maintenance and service. That's why we set the optimal value from 5 to 200 meters. We want wind turbine to be far from highly populated area, so we set the optimal value from 0 to 100. And we want wind turbine to be in area with high wind speed of 6 to 10 meters per hour. Wind turbine had to be outside of protected area. There are 4 different types, gap 1 to 4, and only gap 4 is not protected. So we group gap 1, 2, and 3 as class 1, and gap 4 and no data as 5. And finally, wind turbine had to be close to transmission line to transfer energy with optimal value of 0 to 500 meters. And then we use this output from reclassify and plug them into weighted sum. We set wind speed at 40%, protected area as 30, transmission line as 20, and population and row as 5. Our last step was to reclassify weighted sum output to produce either optimal or not optimal location, and this is our result.
After performing the suitability analysis, we calculated that there was a total of 494 square kilometers of suitable land, mostly on the northeast and southeast quadrants of the map, symbolized in green. The available optimal land covers a large portion of San Diego County, more than is needed to power the plant. To power the Carlsbad desalination plant, in addition to the proposed solar projects, which equates to 161 million watts of energy, only 21 wind turbines are needed, which equates to 589 million watts of energy. One wind turbine requires 1 square kilometer of land. Therefore, 21 square kilometers of land are needed for these turbines. One issue with our geospatial analysis is the issue that many wind projects face: the issue of bird collisions. California songbirds are endangered. Allen's hummingbird, as shown in the map provided by Cornell Lab, has a migration that covers most of Southern California, which includes the entirety of San Diego County. They begin their migration in early December, arriving in their desired location in January. To mitigate this risk of further endangering the population of Allen's hummingbird, the wind turbines would need to be slowed significantly during the migration month or placed in a strategic way that the birds could easily avoid. As a next step to our analysis, we can research the optimal placement of each of the 21 wind turbines and plot them on the map. In our previous project, we turned solar energy into water, and now we have turned wind energy into water, combating the negative outcomes of climate change, scarcity of water, while preventing further warming from occurring using renewable energy sources as opposed to fossil fuels. We would like to acknowledge the GSAL laboratory, Fernanda Lopez Ornelas, and Dr. David Saw, and the MSCM program at the University of San Francisco. Thank you.